Today we're going to be talking about continuity. A function is continuous at a point if its limit is equal to what the function actually is. So think about it as with our limit, we're using data points around where we care about to predict that value. A function is continuous if our prediction matches what actually happens. It's continuous on an interval if it's continuous at every single point in the interval. So we can talk about a function being continuous at a specific point. We can also talk about it being continuous at a whole bunch of points. If it's continuous everywhere that we can plug it in, we say it's continuous everywhere. Let's take a look at this graph. It's our graph that we've used a couple of times in the previous videos. We want to know, is f continuous at 1? Well, our limit as x goes to 1 of f of x is going to equal 1, right? As we're approaching the value x equals 1, we're also approaching the value y equals 1. But the actual f, the actual function, when we plug 1 in, isn't 1, it's 0. So this function is not continuous at x equals 1. It is continuous at a lot of other places though. So for instance, if we're looking at this point where x equals 2, our limit as we're approaching this is 0, and our function itself is also 0. So it is continuous at x equals 2. A sort of rule of thumb way to figure out if a function is continuous is if I can draw that function without lifting up my pencil, then that function is continuous. So we can see as we're coming in from the left-hand side, we're going down this parabola. I can draw this whole parabola without lifting my pencil. So I'm continuous at this whole interval all the way up until x equals 1. But then when x equals 1, I have to lift my pencil up and bring it down to put this dot in at 0. And then I have to lift it back up again to keep on going. And then once I keep on going, I don't have to lift my pencil again. So I'm still continuous as I keep going down. So I can tell what intervals a function is continuous at. I mean, we just saw it eyeballed on this graph. We can tell open intervals. That's what this parenthesis means. This means this is the interval, but it does not include b. That's what that open parenthesis means. A square bracket means it's closed. The square bracket means this does include b. So we can eyeball an open interval. I can say, okay, as I'm coming up to this x equals 1, for instance, on this graph up here, this is continuous. And then our question is, does it include the endpoints? Does it include a or b, our endpoints of our interval? And we can tell that if the right-hand limit matches the lower piece of our interval and the left-hand limit matches the upper piece. So let's take a look at this piecewise function. As I'm looking at the first part of this function in between 0 and 1, I can see it's continuous in between 0 and 1 because I can draw that whole line without lifting up my pencil. So I am continuous between 0 and 1, and my question is, do I include those endpoints? So the first thing I want to check is as I'm going to 0 from the right, what do I expect that to be? Well, my right-hand limit there is expecting that function to be 0, and when I plug it in fact is 0. So I can include 0 in my interval. Similarly, as I'm approaching 1 from the left, that limit is 1, and the function itself is also 1. Now notice that the overall limit of 1 doesn't exist because my right-hand limit does not match my left-hand limit. So that function, or that limit, doesn't exist. However, when I'm looking at the endpoints of an interval, I don't care about the limit overall, I just care about the one-sided limit. So as we're approaching from the left, that limit does exist and it matches the function, so we're continuous on this closed interval. As we're looking at the next piece, we're going in between x equals 1 and 2. And here, the right-hand limit, as we're approaching x equals 1, is 2, but that's not what the actual value of the function is. The actual value of the function is down here. So this is an open parentheses. We don't include 1 in that interval. And similarly, as we come down to 2, the function's not even defined at 2, so it can't be continuous at 2. So those are the intervals that this function is continuous on. Okay, so as we're looking at the interactions between continuous functions, this theorem is copied directly from our textbook, and it just says that continuous functions interact the way we'd hope they would. So if I have two continuous functions and I add them together, they're still continuous. If I multiply them, they're still continuous. If I multiply by a constant, still continuous. And this will help us tell whether a function is continuous if its component parts are also continuous. Here's an example of some continuous functions from our textbook. So every trig function is continuous wherever it's defined. So are powers, logs, and roots. So if you see any of these functions, you automatically know they're continuous wherever they're defined. You don't have to prove that to me. So let's take a look at what this actually looks like in action. So here we have this function. It looks pretty gross, sine of x plus the square root of x minus 2. You probably don't want to graph that because, or at least graph it by hand because it's a little messy, but we can still tell that it's continuous because we know that sine of x is continuous everywhere it's defined as a trig function. And in fact, sine of x is defined everywhere. So this is continuous everywhere. The square root, we also know is continuous everywhere it's defined. Where is the square root defined? Well, I can't plug negative numbers into a square root. 0 and positive numbers, totally fine to plug in. Negative numbers, that square root is not defined. So here, I need x to be bigger than or equal to 2. If it were smaller than 2, I'd have a negative number there. So for instance, if x were 1, this would be the square root of negative 1. That doesn't mean anything. All right, so I have two pieces that are continuous. And by our theorem up here, if I add two continuous functions together, still continuous. So where is this function continuous? It's continuous on, well, I can include 2, right? X can be greater than or equal to 2. So anything bigger than 2, also fine. So it's continuous on this interval. The last thing we want to talk about with continuity is the intermediate value theorem. This is a lot of words, but it's a pretty intuitive theorem. So what we're saying with this theorem is if I have an interval, let's say between a and b, and my function does whatever it does in between those, if that function is continuous, then all the points between f of a and f of b have to be passed through, right? I can't teleport and jump over a point because then the function wouldn't be continuous. So I can pick any y value I want. Let's say this is the y value I want. This function has to pass through that y value. We don't know exactly where it'll pass through that y value, but we know it has to hit it or else our function wouldn't be continuous. So this value c, if I were to plug it into the function, gives me the y value that I'm looking for. So any y value in between f of a and f of b, we have to pass through or else this function wouldn't be continuous. This might be a little bit more obvious as we're looking at a graph. So let's go back to our graph from before. As I'm looking at, let's say this piece of the function is in between 1 and 2, it's continuous. F of 1 is 2 and f of 2 is 1. So let's say I want to know, does this function ever pass through the value, what might that be, 1 3/4 maybe? Do I ever get 1.75? Well, that's in between 1 and 2. So I don't know where exactly I pass through 1.75, but I know the function has to hit it, and I know it has to hit it at an x value that's in between 1 and 2. That's the intermediate value theorem. So to recap, a function is continuous if its limit matches its value. So in other words, if we can draw it without lifting up our pencil. We can predict intervals on which it's continuous by taking a look at all the values within that interval. And we can add, multiply continuous functions, still get a continuous function. And the intermediate value theorem tells us that if we have any y value that is in between the y values of a continuous piece of our function, that has to be hit. We can't jump over it.